colligative properties. So colligative properties are properties that depend on the number of particles that are dissolved, not the kind of particle. So it could be sugar, or it could be some other molecule. It's just the number of particles. Doesn't matter what they are. Just kind of weird, right? If we're talking about electrolytes versus non-electrolytes, things get a little different, because if we have 1 mole of sodium chloride, that dissolves into 1 mole of sodium ions and 1 mole of chloride ions. How many moles of particles is that? 2 moles of particles, right? So we'll get to that later. First, we're just going to talk about non-electrolytes. But this is where this really pertains to the lab we're doing today. Why do you add salt to an ice cream maker? If you've ever seen one of those, or used one of those old-fashioned ice cream makers, you know, it's got the bucket in the middle and this churn. Hopefully it's not a hand crank one. And then you put ice around it. But if you've ever not had salt or not thought to put salt in there, it won't freeze if you don't put salt on the ice. Why do we put salt on the ice? Because putting salt on the ice makes the ice colder. Does that seem strange? Putting salt on your potatoes doesn't make them colder. Why does putting salt on ice make the ice colder? Because it changes the freezing point of the water. So it can lower the freezing point of the water from 0 degrees Celsius to approximately -10 degrees Celsius. And you're going to measure that today in lab. So the vapor pressure is also affected. So let's think about this. Here we have the dynamic equilibrium. We have a closed container. We have things evaporating and things condensing. And so the partial pressure of the solvent here is the vapor pressure, right? If we put some solute particles in this liquid, that's going to reduce the number of particles that are at the surface and is going to cause the rate of evaporation to decrease. So here the condensation is happening at the same rate, but these are going to keep going until they become equal. So here we have fewer particles of gas than we did over there by adding solute particles. So they kind of get in the way, right? More fundamental explanation is nature's tendency towards mixing the increase in entropy, right? The spread of energy. So this is something cool you could do at home. So here's pure water in a container and very salty water in a container. And we put both of those containers inside of a larger container. So you could use, drinking glasses or custard cups and your mom's pie plate. Not pie plate, cake cover thing. I don't have one of those, so that doesn't work for me, but something like that. If you wait, what happens is that later, this beaker has less water in it, and that beaker has more water in it. How did the water get there? It went through the air. Doesn't that seem crazy? It happens really slowly, but even if you had the patience to sit there and watch it, you wouldn't be able to see what's happening. But what's happening is you've got evaporation here and condensation there. So the vapor pressure is less for the solution. So we're going to get a net movement of water over here. We can also think of the tendency towards mixing, right? So you had those two gases and you remove the barrier and they mix. You have the two fresh water and salt water, you remove the barrier, it mixes, right? Well, here, the fresh water and the salt water are trying to mix. It's just taking longer. Raoult's law quantifies vapor pressure, and this is relating to that quote at the beginning. So this is Raoult's law. The partial pressure of a solution is equal to the mole fraction of the solvent times the original partial pressure, the partial pressure of the pure solvent. And here we're using mole fraction rather than mass or concentration or something, because it's just the number of particles. It doesn't matter what they are. So we see that the vapor pressure is directly proportional to the amount of solvent in the solution. If there's more solute, the vapor pressure is lowered. And vapor pressure lowering, delta P, they're taking this and doing some math on it, and you get the partial pressure of the pure solvent times the mole fraction of the solute. Good news, these are not equations you need to memorize for the fourth exam. So this one, calculating the vapor pressure. I'm not going to do this whole thing either, but the vapor pressure of the solution is going to equal the mole fraction of the solvent, here is water, times the vapor pressure of pure water. So we're given the vapor pressure of pure water. We have to calculate the mole fraction. We already calculated a mole fraction, so I'm not going to do the whole thing again, right? But the mole fraction of water is the moles of water divided by the moles of water plus the moles of ethylene glycol. We'll call him EG. So that's just tedious, right? You've got grams and you calculate moles. You've got grams and you calculate moles. You put them in here, you get a number, and that's this number. And then you multiply by that. If the solute is something that's volatile, that will evaporate, then it is also going to have its own vapor pressure, and that will add to the vapor pressure of the solution. So an ideal solution follows Raoult's law at all concentrations. So the total vapor pressure of the solution is equal to the pressure of one component plus the pressure of the other component. But there are solutions that are non-ideal. So this is how things are supposed to behave, right? So if we look at the partial pressure of A as a function of its mole fraction, as the mole fraction increases, the partial pressure of A increases. Here we've got the partial pressure of B. When there's no A, this is initially high, and as we move towards more and more A until here we have 0 of B, then its pressure is 0. The pressure of the solution is the sum of those, and that gives us a straight line. Deviation is going to look like this. So here we have strong interactions between the solute and the solvent. They really like each other. They don't want to evaporate. And so what we'll see is when they're both present, the vapor pressure is lower than we expect, because the vapor pressure of part B is lower and part A, and so when you add them together, it's lower. Here, they're in a solution, but they really don't like each other very much, so they're really eager to get out of there. They're happy, it's like, hey, I volunteer, I want to evaporate, right? So now the vapor pressures are going to be higher than expected. I'm not doing that one. It's incredibly tedious, and I don't think it's that useful. If you want to see it, there are old videos where I did do that. My poor students. Freezing point depression. Okay, this is what we need for lab today. So this is a phase diagram. Here we have 1 atmosphere, and this line here is describing where the temperatures at which the water would freeze, right? So this is the transition between melting and freezing. So here, this is, for water, this is going to be 0 degrees Celsius. vapor pressure lowering happens at all temperatures. And so the vapor pressure, let's see how to explain that. Well, this curve moves out. And here, the curve between the liquid and the gas, the fusion curve, vaporization curve. This is the fusion curve, this is a vaporization curve. This also moves out. So we have the effect that the boiling point goes up and the melting point or freezing point decreases. So we have freezing point depression and boiling point elevation. So I used to have a hard time remembering those. What worked for me is that these temperatures move away from each other. The purpose of adding antifreeze to your radiator is to expand the temperature range over which the water stays a liquid. You don't want it to freeze solid and burst your radiator. Not a big concern here, but in Minnesota it happens. You also don't want it boiling at a lower temperature because then it's not effectively cooling your engine anymore. If that doesn't work for you, maybe this does. If you don't like cold weather, when it's freezing you might be a little depressed. If you think of boiling, somebody being hot, right? They're hot-headed, they're elevated emotions. I don't know. Take it or leave it. Anyway, there's an equation for this, of course. So the freezing point depression, delta TF, that's the change in the freezing point. And I'm sorry about this, but they didn't ask me. They always report this as a positive number, even though the freezing point depression should be a negative number. I guess they didn't want to deal with the negative in the equation. There it is, I'm sorry. It's equal to the molality of the solution times a constant, the freezing point depression constant. Very clever name. We use molality here because here we are looking at solutions at different temperatures, right? And so we need that concentration to stay the same. So here we have a table showing freezing point depression constants for different liquids. So here's the one for water, 1.86. Units are degrees Celsius per molal. This is also giving us the boiling point elevation constant, which is, we'll talk about that next week. So here, calculate the freezing point of a 2.6 molal aqueous sucrose solution. So freezing point depression, delta TF, is equal to the molality of the solution times the freezing point depression constant. This is just a refreshing change. They're not making us calculate the molality. They just told us what it is. Thank you. So 2.6 molal, and the freezing point depression was on the previous page. It's 1.86 degrees Celsius per molal. So we multiply 2.6 times 1.86, 4.836. And the unit would be degrees Celsius. Are we done? No. It's really tempting to say this is the answer. But it wants the freezing point, not the freezing point depression. So this is the freezing point depression. This is how much the freezing point changes from normal. So we're not done calculating. And this can get a bit confusing because there's, negatives and stuff. So here's my thermometer. What's the normal freezing point for water? 0. So there's normal, 0 degrees Celsius. The freezing point depression, does the freezing point go down or go up? It goes down, right? So here's our new freezing point, and the difference here is 4.836 degrees Celsius. So then this temperature is negative 4.836 degrees Celsius. This only has two sig figs, and so on the computer this is expecting you to say negative 4.8 degrees Celsius. And this thing, you know, asking for the freezing point when the equation calculates, answer is negative 4.8.